Hey guys, Mr. Betts here. I want to talk to you in this video about something called improper integrals. So improper integrals are going to be a type of integral that represents an area that is unbounded either horizontally or vertically. So let's take a look at what that might look like. So it's going to be an integral that either one or both limits, so the lower limit or the upper limit is going to be infinite, or it's going to have an integrand that is unbounded. So this function here is unbounded within the interval. So let's take those kind of one at a time and talk about why they're improper and how we can handle that. So the one that is infinitely wide is going to be kind of easy to identify because one of our limits is going to be infinity. And so the idea here is that the area that we're finding has an infinitely wide region, but since the rectangles that we're using to find that area are getting shorter and shorter and shorter and approaching a height of zero, that infinitely wide region could actually have a finite area. It turns out that the area here represented by this infinitely wide integral is a finite area. The other type of improper integral that we're going to see is not as easy to identify. So if we didn't have the graph here and we just looked at the integral, we might not notice at first that the integrand 1 over square root of x is undefined at 0 and has an infinite discontinuity at 0. So that vertical asymptote that we get here is the same sort of thing that we had with a horizontal asymptote here. And again, since the height is infinite, but the width is approaching 0, at least for the rectangles as we approach that left limit, are getting infinitesimally wide, so really, really narrow, then we could get a finite area. And indeed, this particular one is finite. Now, not all improper integrals are going to be finite. Some improper integrals are going to give us an infinite area still. So we are going to have to go through a process to evaluate these improper integrals. And there's a very important step in that process. So in order to evaluate an improper integral, we must first write it as a limit of a proper integral. So a proper integral is going to be an integral where all heights and widths are finite. So in the first type of improper integral, where we have an infinite limit, what we're going to do is we're going to write it as a definite integral with a variable upper limit. And we're going to say, okay, if we're finding this area here as x goes to infinity, what we're going to do is first evaluate a definite integral for some variable k, and then we're going to look at what happens as k approaches infinity. So this integral right here is a proper integral because it has a finite ending, but then we're going to look at the limit then as k approaches infinity, and if that limit exists, then that means that the area represented by this improper integral is going to be finite. If we have an infinite discontinuity on the interval, we're going to do the same sort of thing, but it's going to look a little bit different. So the infinite discontinuity that we have here, I'm going to say, is at the point x equals c. And so what we have to do here is we have to split up our integral into two separate integrals. If you remember our properties of integrals, we can rewrite an integral from a to b as an integral from a to some number in between a and b, and it doesn't even necessarily have to be in between a and b, plus the integral from c to b. Now, I know this is an informal notation here, but the idea is we can split it up into two separate ones. So if the infinite discontinuity is somewhere internal on the interval, we're going to have to break it up into two separate ones. And then notice the way we rewrite it into a proper integral this time is we go from a to some variable. I chose r here, but it doesn't have to be r. So I'm going to choose r, and r is going to be approaching c, but we're going to find the area of a proper integral, which is finite, and then we're going to look at what happens as r gets closer to c. So that's the limit here, and notice that the limit is approaching c from the left side. that one-sided limit here is really important because we have to approach from inside of the interval. And so then we look at the limit as S approaches C from the right. So on the right side, we're looking at this part over here, and we're going to pick some number that we know is going to give us a finite value because it's a proper integral, and then we're going to look at what happens as S approaches C from the right side. So notice the one-sided limit there. A lot of times what's going to happen is either A or B, either one of the limits is going to be the infinite discontinuity, so we don't have to split it up. So for example, if this was the integral from A to C, then we would just have this, and we would not need the second part. So that's if C is the infinite discontinuity. So that's going to happen more often than not with these second types of improper integrals. But if there is an internal infinite discontinuity or vertical asymptote, we do have to write it as two separate limits. If we do have two separate limits, both limits have to converge for the integral itself to converge. So if either one of these limits diverges, then that means that the whole thing diverges. So if one diverges and one converges, then this still diverges. Okay, so it does have to, both of the limits have to converge for the whole thing to converge. Last thing I want to mention here, I already hinted at this. So if the limit does not exist, or if the limit is infinite, so remember we are going to rewrite these problems as limits. So if it's infinite or does not exist, then the integral diverges. So diverge and converge are terms that we've used for limits before. Now we're going to start using them for integrals also. Technically, integrals are limits anyway. So when an integral has a value, it's because a Riemann sum converges, but that's besides the point. If the limit converges, then the integral converges because the area is finite. Typically, if an integral is going to diverge, it's because the area is infinite, but we are going to see in one of the examples in a later video where the total area is not necessarily infinite, but still it's going to diverge. And we'll talk about why when we get to that example.